Topic 5, work, energy, power. In dynamic, we study force causes acceleration. That means you are looking at resultant force. Forces in equilibrium, which we studied last week. Forces acted, then forces acted on the area. Right? Forces in equilibrium, there's no resultant force. And for this topic, topic 5, we look at force can do work. And then next topic, topic 6 is deformation. Force can increase or decrease length. Okay, so we are looking at forces can do work. That's the syllabus. Okay, what are we going to cover? Energy conversion and conservation, forms of energy, energy conservation 5.1, kinetic and potential, work done in various situations. Then we look at efficiency. And after that, we look at specifically potential energy and kinetic energy. And then we derive the formula. EK is half mv squared. And then distinguish between different form of potential energy. Derive and recall potential energy, gravitational potential energy, MGH. And then we will also cover power, right? And define power as work divided by time. And then derive this equation, P equals to FV. Don't bother about the textbook, you can use your own textbook. Okay, forms of energy, we got light energy, you know, different form of energy, kinetic energy, potential energy, thermal energy or heat energy, electrical energy, chemical energy, nuclear energy. And then when we use mechanical energy, it means kinetic and potential energy. Okay. Conversion and conservation energy, dropping a ball from a tall building. Initially, the ball has potential energy. When we drop the ball from a tall building, it has potential energy. Right? Potential energy is maximum. The ball is not moving, so no kinetic energy. As the speed increases, kinetic energy increases, potential energy decreases as height decreases. Work done against air resistance is transformed into thermal energy. Right? There's going to be work done against air resistance. So as the speed increases, the work done against air resistance is going to be greater. So you should be able to write out the formula. Right? The equation, total energy at any time is potential energy plus kinetic energy plus Q. Q is your thermal energy. Right? Height decreases, potential energy decreases, speed increases, kinetic energy increases. Air resistance also increases because the speed increases, the air resistance increases. Work done against air resistance transform into heat energy. At any time, the equation is the same. Right? I'm just repeating the same thing.
Can I ask why is there suddenly heat energy?
There's friction, air resistance. Where there is opposing force, there's going to be work done against opposing force. So that becomes heat energy.
Oh, is it like the asteroid when they fall, the time got fire?
Just
Is
like
it because like that?
when you move on the ground, there's going to be friction. So that the body, when you
Oh,
touch the body, the tire or the tire of the car, the tire of the car will be warm, the road will be warm, because they're going to be rubbing. Anytime there's
also is rubbing against air molecules, air particles.
it's going against
Oh, okay.
air particles, so it's giving air particle is opposing it, so there's going to be energy given to the air particles. So,
Hmm.
okay, energy conversion, changing forms of energy. In a car, chemical energy in petrol is converted to mechanical energy and heat energy. So you should be able to write down the conservation energy. Chemical energy equals to mechanical energy plus your heat energy. When we say mechanical, it can mean kinetic and potential. Right? Heat energy is because there is going to be work done against friction and air resistance. And energy from the sun is nuclear energy to radiant and heat energy. So all these we summarize as conservation energy. Oops, sorry. Principle of conservation of energy states that energy cannot be created or destroyed. It can only be converted from one form to another. Total energy in a closed system is constant. It doesn't change in a closed system. Right? It changes from one form to another. So we can summarize it as E equals EK. EK is kinetic. EP is potential. U is internal energy and other form. And it's constant at any time. In any process, one form of energy is transformed to another. If you are interested in mechanical energy, then we write EK plus EP. This one we are not interested. We will be interested in A2, principle of conservation of energy and mass. Right, so now we replace our conservation of energy with conservation of energy and mass. And then where there is a change in mass, c is the speed of light. Total energy and matter in the universe is constant. Matter can be transformed into energy and vice versa. That means energy can also transform into matter. This law tells us that creation was completed at one time in the past. Application. Right, we won't go into much detail. Basically, when physicists first study radioactive decay of beta particle, they find that there's a missing energy. They basically study as two particles involved. Then the theoretical physicists, from the result of conservation energy, there must be another particle called neutrino that's taking the energy away. So they predict it first, and 25 years later, the experimental able to confirm neutrino. So beta particle decay is a 3-particle decay, not 2-particle decay. Okay, we start with definition. Work is force times distance moved in the direction of the force. Both force and distance moved in the direction of force, or we call displacement, are vector quantities. Right? The distance moved has a direction. We can show you the diagram. Distance moved and the force are in the same direction. So unit, go to the formula. F times x. X is displacement. F is the force. Force is in Newton. X is in meter. So the unit is Newton meter. Or we give it a special name, Joule. Or kilogram meter square S minus 2. So 1 Joule is 1 meter times 1 Newton. It's a scalar quantity. How much work is done depends on two factors. Right? From the formula, size of the force, bigger the force, greater the work. Distance moved, The further the object move, the greater the amount done, the greater the amount of work done. Right? And that's the definition of 1 joule. 1 joule is defined as the amount of work done when the force of 1 Newton move a distance of 1 meter in the direction of the force. Okay, what happens if the force is at an angle? Like in this case, a person is pulling with a force F and is making an angle of theta with the ground. So we just use the definition of the force. Force must be in the direction of the displacement. So it's force cos theta, right? Force cos theta times your x. The work done is your force in the direction of the displacement times the displacement x. Fx cos theta. Right? Either way, you can either think of it as this is our original case, displacement, force, that's the angle. So you can either think of it as, in this case, we can view the formula as force times distance move in the direction of force. That means we resolve the distance move or the displacement into the direction of the force, which is x cos theta. Or we can think of it as we have done before just now. That's the displacement. That's the force. So we resolve the force in the direction of the displacement. Perpendicular direction doesn't do any work. Okay, so both formula are the same. Okay, how to draw graph? Work by a constant force. That's the force. That's the distance move or displacement. That's the force. So area under the graph. Work done. Area under the graph. F times X. Now we can also draw the work done. Work done. And then distance move. So we can see that it is going to be a straight line. This is the equation. Or we can rewrite the equation. Right? W equals to Fx. That's the work done. W. That's your X. So F is given by the gradient of the straight line. Compare with the equation of straight line, y equals to mx. Right? So force can be obtained from the work distance graph as gradient. Right, this is A2. I just go briefly with you. Constant pressure, the volume changes from this initial volume. Frictionless piston, there's a piston, is movable. So the pressure applied to it increase the volume. Work done by expanding gas at constant pressure. P is delta V. Delta V is the increase in volume. P is the pressure, constant pressure. Work done on gas. Right? We distinguish the type of work done. Work done on gas is compression, adding energy to the gas. Work done by gas, expansion, is the gas that expand. So that is called work done by the gas. Right? We derive it same. That's the original volume. It changed by delta D, the distance. Pressure stay the same. So work done is with our definition F times X. Right? Then use the definition of pressure. Pressure is force divided by area. So our force is pressure times area. Pressure times area. Area times distance is volume. That's how we derive it. And we can draw the graph. Right? Constant pressure, horizontal line. is the volume axis. So that area there is P V2 minus V1. Anything not clear? Anything you need to explain further?
Okay.
Okay. Basically, we draw the arrow to show it changes from volume V1 to V2. Efficiency. Practical devices. Practical devices can be a car, can be a lamp. You can see the incandescent light bulb uses about 5% of input energy and 95% wasted heat. That's why we hardly use it anymore. This is when I was your age, still use it. Then fluorescent lamp came along. It's cooler. Right? That's the device, a thing that made for a particular purpose. An invention or contrivance, especially a mechanical, electrical, that means basically a device changes from one form of energy to another form of energy. Right? Take in energy, it's called energy input, and then it does work. There's the energy output, and then it converts to other forms of energy. Right? So basically, electrical energy for a lamp, electrical energy taken in, there's the input, and gives out light. Light is the useful energy because it helps us to see. So we call it energy output, E out. Then we've also experienced heat, thermal energy. This wasted, doesn't benefit us. It just keep the room warm, make us uncomfortable. Or we can represent it in a different way. Energy conversion device. Left hand side, energy input. Right hand side, energy output. And then downwards there, energy wasted. So we can define efficiency as ratio of work done, energy output over energy input, right? Given by formula times 100% if you want percentage. Energy output is the useful energy that benefit us. Example, a moving car. The heat energy is wasted energy. Wasted energy usually is lost as heat due to work done against friction, like a car. The tire becomes warmer, it doesn't benefit us. Right? So we can have an energy conversion device, energy input, energy that go in, energy output, useful energy, we can write in the equation form, and then energy wasted. That's our conservation of energy. Right? That's our efficiency formula. So usually, because of energy wasted, efficiency is going to be less than 100%. We can never get 100%. Another way of showing is to use Sankey diagram. Right? Left-hand side, energy input. Where does it go to? Energy output and energy wasted. Right? Basically, Sankey diagram summarizes all the energy transfer taking place in a process or in a device. Ticker, right? This particle arrow, the greater amount of energy involved. That means the energy input, most of it go to energy output, very little wasted. That's what the diagram tells us. Right? A point to ponder. Force causes acceleration, right? Causes acceleration, but it also moves the object at distance x. Rough ground means there's going to be friction, F. Force causes the object to move a distance x. The velocity increases to v. Initially, it's at rest. So you should be able to write the formula for conservation of energy. I can think of a car if you don't want the block. Rough means presence of friction. Force applied. For a car, it's a thrust by the engine. X is the distance move or displacement. F is the friction between the block and the ground. So you should be able to write down work done by applied force is the energy input. Work done against friction is the energy loss as heat. Gain in kinetic energy, then you should be able to write down in formula, write down alternative. There's the equation Fx equals to small f times x. That's your sorry, it's just the thing is blocking the. Okay, that's the equation. Okay, should be able to write down the four in words and write down the equation. Let me see, is the energy input. Let's work done against friction. There's an increase in kinetic energy. Right? Sometimes, if you prefer, right, you can either use the formula, or draw triangle, where you take the efficiency and energy input, put it at the bottom there, and then useful energy is at the top there. So if you want useful energy, you cover it up, efficiency times total energy. Or if you want efficiency, is useful energy divided by total energy input. This is for your info. We won't go into much detail there. Right? It's just to show most of the energy is lost as heat. Only 10 joule. Right? 90% is lost as heat. Okay. Define power. Work done per unit time. There's a formula. You can write it as a formula. W over time, but not as a short form case. Right? Used to be defined as rate of energy conversion. Now, if you look at older textbook, work is in joule, time is in second. So it's joule per second. We call it watt, capital W. It's a scalar quantity.
Teacher,
Yeah.
I think your screen is frozen.
Say again.
Your screen is frozen. It's not showing the power one.
Hey, what is wrong? Let me try again.
Okay.
Does that help?
Yeah.
Okay, good. Tell me if there's a problem. Now we derive power is force times velocity or speed. Right? We look at an object. There's a force applied, F, and then there's friction. And then because of force and friction is moving at constant speed, constant velocity. So our power is force times velocity. We're going to derive that. Okay, so the object is moving on a rough ground. There's friction. The force is capital F. Friction is small f. So it's moving at constant velocity. So we always go to definition. When we derive, we go to definition. Definition is force and displacement. Power is work done over time. Work done equals Fx divided by time is t. Right? And velocity or speed is x over t. So it's like t equals to Fv. Okay, okay, so these are various ways of writing the same thing. Right? We can use power instead of energy. We can use power. Same thing. Conservation energy, power input goes power output goes to power wasted. Efficiency formula, the same thing. We just use power output or power input times 100%. For efficiency, as I say, it will never be 100% because there's always presence of friction between moving parts. Thus, energy is lost as thermal energy. Right? Maximum we can go is 100% or 1. For 100% efficiency, it means that the power output is equal to the power input. Efficiency of the device is usually less than 100% due to energy loss as heat or other forms of energy. Okay, sitting, reading, or watching TV, your power rating basically tell you the maximum power used by a device. So the maximum power you use is 100 for sitting. It can come out like light bulb. They can ask you the power rating of light bulb 60, 100, 120. Right? Kettle also can come out. Whereas for heating is higher power rating is higher. Okay, so this one you need to memorize Okay, this one we will I just explain to you roughly. Basically, when we use fossil fuel, it produces carbon dioxide. So it's going to cause heating of the atmosphere, and as a result, the ice in Arctic and Atlantic will melt. So the water level will rise. So it poses danger to those staying in low-lying area in coastal region So we have to reduce the consumption of fossil fuel. That's why we are going to renewable energy. So for our part, we can save money by using less electricity. When we are not using light bulb, in our home, we switch it off. Minimizing heat energy loss from building. This is for where you're in a cold country. You use a lot of heater to heat up the room. So you want to minimize the heat loss. Economic use of appliance, not using it, switch it off. If you want to prepare a cup of tea, just use sufficient water. Don't boil a whole pot of water. Minimize energy use for lighting. Right? Not using it, switch it off. Okay, we won't bother about that. This is to show you the efficiency is usually very low for different devices. Okay, any question to ask? Any comment?
No.
Okay, if not, let's carry on. Potential energy and kinetic energy. Right, that's the syllabus, 5.2. Energy is the ability to do work. So we want to find energy of a device, we let it do work. A moving body has energy because it can do work. Right? Example, a turbine is rotating it, so it's converting wind energy. Okay, 10 minutes time we will end in case we got cut off. A moving body has energy because it can do work. To calculate the energy in a body, we let the body does work. Right? Just like the body got kinetic energy, we let it does work, which we're going to do in a while. Right? So energy equals to work done. Okay, kinetic energy. Kinetic energy is the energy of motion. Kinetic energy of an object is the energy it possesses because of its motion. If it's moving, it got kinetic energy. And you need to memorize the formula and know how to use it. EK is kinetic energy object. M is mass of object. V is the speed of object. In this case, the mass of the person, M. Okay. So how to derive it? We can think of the body has a mass m initially at rest. Then we apply a force that moves it a distance x. Increase the velocity to v. We are basically saying that kinetic energy equals to work done. So we are going to derive for linear motion, initial speed, initial velocity is u equals 0. Then final velocity is v, distance move is s. A is acceleration. So we use v squared equals u squared plus 2as. Our u equals to 0. Our s, we replace it as x. And we want ax. We divide by 2. So it's half v squared. That's part of the derivation just now. Now we are going to use the kinetic energy equals to work done. The work done is force and distance, force and displacement. Force is ma, displacement is x. So ax, which we have got from here, ax is half mv squared. Okay, any comment? You need to know how to derive. That's required of your syllabus. Okay? Okay, okay, okay. Right, so we have a formula. We can write down that gain in kinetic energy equals to work done. If initial speed is u, final speed is v, then the final kinetic energy minus initial kinetic energy equals to work done. Potential energy is stored energy available to do work. There are different types: chemical, elastic, and gravitational potential energy. Gravitational potential energy, right? Object at a height h above the surface of the earth. Object has a mass m, height is h, so gravitational potential mgh. Memorize it and know how to use it. So g depends on mass of the body, height of the object, gravitational field strength. Right? So we are interested near the surface of the earth. Right? For A2, we are interested at distances not near the surface of the earth, where our g changes. So here we are interested g constant. Okay, same thing, we are going to derive. So we consider the object of mass m at the surface of the earth. We raise it up to a height h. So our work done. What is the force? Force times distance move. Distance move is the height. So the force is mg. Is the weight times height. So an alternative way of writing it is change in potential energy equals to mg delta h. You can call this one delta h. If you don't want to call it h. Right? So we are just using work done equals to gain in potential energy. Okay, Object at high potential energy will move to one of low potential energy. That's why when you drop a ball, the ball will move to the surface of the earth. This is for your info. Gravitational potential energy, store energy due to its position above the surface of the earth. Need to know how to define. Elastic potential energy, store energy due to material being stretched or compressed. Right? One is because of the height, one is because it's stretched, compressed. Okay, so whether you drop it from a high h or the object move down a slope that is smooth, or it go down in steps, different step, but the height is the same, potential energy is still the same. So that's this one summarize for you what we have covered. Your own mind map to help you remember all the things that you need to remember. Okay, energy transformation, a force applied to object, move it from initial velocity u to final velocity v. So you should be able to write the equation, energy equation. Right? Work done equals to gain in kinetic energy, Fx, F, work done, Fx, final kinetic energy minus initial kinetic energy. Or we throw out a ball. The ball has a mass m, initial speed where you throw it up is u, velocity, and final velocity is v, height is h. So where you throw it, it has high kinetic energy because high velocity. Then when you move up a high h, the velocity decreases, so it's low kinetic energy. But where you throw it is low potential energy, increase the high potential energy. So gain in potential energy. So you should be able to write down the equation. Anything you want to clarify?
So the higher
it goes, the greater
the higher potential energy.
energy. The higher it goes, the less kinetic energy it will be. The more kinetic energy is
but higher PE, higher potential energy.
So with maximum height, all the initial kinetic energy is converted into potential energy.
Oh, okay.
Yep. Anything you want to ask, clarify? We got slightly more than a minute. So I think no point in teaching it anymore. Might as well stop here. Anything you want to ask or clarify?
Don't know.
Okay. So I will stop here and then you can try the question. Then I will tell you when I'm ready to start again. Okay?
Okay.